Carbon dating is used to date anything that used to be living, any organic materials, as old as 50,000 years. The atmosphere contains mainly carbon-12, which is the stable isotope of carbon, but it also contains a tiny amount of carbon-14, which is a radioactive isotope of carbon with a half-life of 5,700 years. Both carbon-12 and carbon-14 are taken into living materials by respiration, and the ratio in the atmosphere is almost constant at a ratio of 1.3 times 10 to the minus 12 carbon-14 atoms for every one carbon-12 atom. So when something dies, the number of carbon-12 atoms stays constant, but the number of carbon-14 atoms decays exponentially with a half-life of 5,700 years. So how is carbon-14 made? Well, it happens in the upper atmosphere, when high-speed protons in cosmic rays collide with atoms, producing neutrons. The upper atmosphere is about 80% nitrogen-14, and the neutrons that are produced collide with the nitrogen-14 nuclei, forming carbon-14 and a proton. Carbon-14 decays by beta emission. Writing the carbon first and then the beta particle as 0 minus 1e gives us nitrogen as the product, and of course we need an anti-lepton neutrino to balance the lepton number. So how do we actually use carbon dating to date objects? Once an object dies, it will no longer be taking in carbon-14 by respiration, so the number of carbon-14 atoms will start to decay against time, and so the activity of the sample will decay against time. So the activity of the sample you're testing to find the age will depend on the number of radioactive carbon-14 nuclei. Using A equals A naught e to the minus lambda t, where A naught is the activity of the sample when it was alive, and A is the activity now when you're testing it. A naught is the initial activity, which was the activity of the sample when it died. Now we can estimate it pretty accurately by measuring the activity of a fresh sample of the same material, e.g. wood or bone of exactly the same mass as the sample we're testing. Rearranging the exponential equation and taking logs to the base e gives us an equation for time. So let's do an example to see how we can apply this. Suppose we found a wooden Egyptian axe in a tomb which has an activity of 0.38 becquerels. If we then tested the activity of an identical mass of wood cut from a living tree and found it was 0.65 becquerels, calculate the age of the axe. Firstly, we need to find the decay constant using log 2 over t to the half. We can keep t to the half in years, which will give us a decay constant in years to the minus 1. Using our rearranged equation for t by taking logs to the base e gives us an age of approximately 4,400 years for this axe. You also need to understand some limitations of this method, which will cause some uncertainty in our calculated values of age. The first one is, it assumes that the rate of carbon-14 to carbon-12 is the same now as it was then, because we're using a fresh sample to find the activity of the sample when it died. Secondly, in the past 100 years, we've been burning a lot of fossil fuels, which increases CO2 emissions and therefore reduces the ratio of C14 to C12. We know that C14 is created in the upper atmosphere by cosmic rays, so the ratio of C14 to C12 is also affected by solar flares, which increase the amount of carbon-14. And finally, because we're dealing with such tiny amounts of carbon-14 in a sample, the activity is very low and is similar to background count. So now let's have a look at how we can date rocks. Of course, we can't use carbon dating because there's no organic material in rocks. Some rocks, when they're formed, contain radioactive materials. Over time, this radioactive material is going to decay into a stable isotope. For instance, rubidium-87 decays into strontium-87 with a half-life of about 49 billion years. If we take a sample of the rock and measure the ratio of radioactive isotope to the stable isotope it produces, this allows us to age the rock. If we plot the number of nuclei against time, you can see for the radioactive isotope, this is going to drop from 100% to 50 to 25% every half-life. As the radioactive isotope produces a stable isotope, the whole amount still needs to be 100%. So you can see the stable isotope produced grows as shown. So let's now do an example. Suppose a rock formed towards the start of the Earth contains rubidium-87. This emits beta minus radiation, decaying to stable strontium-87. The half-life of rubidium-87 is 49 billion years. If we tested a sample of this rock and found out it contains a ratio of 3,000 nuclei of rubidium-87 to every 196 nuclei of strontium-87, we can calculate the age of the rock and hence estimate the age of the Earth. N0 will be the initial amount of rubidium. Seeing as we have 196 nuclei of strontium, which were originally rubidium, then the total number of rubidium nuclei for this same ratio will be the two added together. Next, we need to calculate the decay constant. We can keep t to the half in billions of years. This will give us a time in the end in a unit of billions of years. Using n over n naught is e to the minus lambda t, and taking logs and rearranging gives us the age of the rock and an estimate for the age of the Earth. So another example looks at using percentages. So imagine a rock contains 0.3% strontium-87 compared to rubidium-87. Calculate the age of the rock if t to the half for rubidium-87 is 49 billion years. So again, we can calculate decay constant first. Secondly, the ratio n over n naught is going to be the percentage of rubidium-87 left. Because 0.3% of it has turned into strontium-87, we'll have 99.7% left, which is 0.997. By taking logs to the base e and rearranging for time gives us a value for the age of the rocks.